A toy car of mass m is held at rest against a compressed spring. When released, the car travels around a loop. Determine the speed of the cart as a function of the angular position of the cart on the loop. Let straight down be 0 degrees. So we're determining the speed as a function of the angular position, theta, the spring constant k, the initial compression of the spring s, h, which is the height of the loop, m, the mass of the car, and little g. Assumed friction is so small that it can be ignored. So if we do the free body diagram for event 1, when the cart is against the spring, we have the force of the spring acting on the cart, we have the force of gravity acting downward, and the normal force acting upward. At event 2, when the car is at an angle theta, we have the force of gravity acting downward and the normal force, which is perpendicular to the velocity. So we never have to worry about the work done by the normal force in this problem because it's always perpendicular to the direction that the car is going in. So work done by forces other than the force of the spring and other than the force of gravity is 0. So that gives us this for our work-energy relationship. When the car is released, the velocity is 0. And let's say that the initial height is 0 also. We have initially elastic potential energy, but after the cart is released, when it's going around the loop, the spring is no longer touching the cart, so we don't have to worry about elastic potential energy afterwards. So that gives us initial potential energy is 1/2 ks1 squared, and that's equal to final kinetic energy. And V2, they said, determine the speed of the car V as a function of the angular position, so let's just call that V. That's what we're looking for. We want to find V plus mgh2. The initial compression of the spring is just S. Let's call that S. I can have that in my equation. And I can have m in my equation. I can have g in my equation. So I have to figure out what h2 is. So if the cart is at an angle theta, so let's say the cart is currently here, this angle is theta, this height here is h2. I want an expression for that height. The distance from here to here is capital H, which means from here to here, that's the radius, which is half of h. This distance from here to here is also the radius, and the radius is half of the height. So this is h divided by 2. I can find this by doing h over 2 times cosine theta. So this is h over 2 times cosine theta. So finally, this distance that I'm looking for is h over 2 minus h over 2 cosine theta. Or you could say h over 2 times 1 minus cosine theta. So let's put that in here. We have 1/2 ks squared is equal to 1/2 m v squared plus m times g times capital H times 1 minus cosine theta. Solving that for the speed, we bring this over to the other side. So we have 1/2 mv squared is equal to 1/2 ks squared minus mgh times 1 minus cosine theta. We multiply both sides by 2 and divide both sides by m and take the square root. Multiplying by 2 and dividing by m gives us, for the first term, ks squared divided by m. Multiply both sides by 2, divide by m, and we get, oops, this was supposed to be h divided by 2. So when we multiply by 2, that goes away, and divide by m, so we get g times h times 1 minus cosine theta. Okay, so if s is equal to 0, so that means the spring is not compressed to begin with. What is the velocity equal to? The spring is not compressed. When you release the cart, it does not go anywhere, and the velocity is equal to 0. If s is equal to 0, this is 0, And the angle would always be 0, so if we say that, then yes, it agrees. Or it gives us something imaginary if you say the angle is not equal to 0, because that is not actually a solution. So let's say that. If k is equal to 0, this is like not having the spring there, which is similar to what we had in this first question. So the velocity should be equal to 0. The spring would not exert a force on the cart. Does our function agree? Yes. So long as you say theta is equal to 0 degrees. Otherwise, it gives you something imaginary because theta actually cannot be equal to anything other than 0 degrees. If theta is equal to 0 degrees, what should v be equal to? Well, that would be if the height never changes. So that would be what we get by solving this equation without the second term here. So we'd have 1/2 ks squared is equal to 1/2 v squared. That would give us v is equal to the square root of k over m times s squared, or you could say times s. Does our function agree? It should. If theta is equal to 0, we have 1 minus 1, and so that just gives us what we had there. So yes, it agrees.